All right, any other questions? Like I say, I want to talk about delete and I want to talk about breadth first search, but other questions?
For the SLP final upload,
Mm-hmm.
do we need to make changes to our previous one, or what's the...
Download the template from Canvas, put your information into it, and there should be 10 weeks worth of changes, right?
Yep.
So whatever progress you've made. And the fall upload was basically a proposal for a project. This is basically a status of where you are now, which is moving towards some kind of prototype, probably in now or spring. Hopefully you've got something like a prototype or lessons learned if you decided you need to go in a different direction, right? What do you discover and so on and so forth.
Yeah. Our project, we made some semi-major changes. So if we did make some pivots because of a certain situation, that's okay.
Yeah, you can talk about that in there too. The format, there's a template there that you can fill in the different fields of, but I don't want you to feel bound by that particular set of section headings and so on and so forth. Whatever is going to make sense for your project, where it is now and what the progress has been, go ahead and adjust as appropriate. Yes?
So in the PowerPoint, it actually says that we need to upload two things, a dash sheet and report to Moodle.
To Moodle?
Yes, that's what it says.
Oh no, we don't want that.
They just figured it meant to whoever professor. We might have to do it like 15 pages at the
Are you reading the instructions on the PowerPoint? Ignore that.
Oh, okay, so we
Yeah.
just upload that.
Just upload that to Canvas.
Okay.
Yeah. I don't think we've updated those instructions in a while, and we probably should, or just get rid of them because the instructions are on Canvas. Yeah, take that, fill it in, save it as a PDF, upload the PDF, one page to Canvas.
So, one of the things that wants is a competitive analysis.
Mm-hmm.
I wonder if you went over this last quarter. Does it want you to think like, would this work in the real world or something?
So you're implementing a solar-powered mole repeller, okay? Because you've got moles in your garden. If you've got 80 mole holes, you probably have one mole. They're like really frightening. So what's the competitive analysis? Are there mole repellers out there? Yes, there are. You can buy one and you plug batteries in and it makes an ultrasonic sound that scares away the moles, right? But the batteries wear out after 2 days. And this costs an average of $15 billion a year to buy batteries for the mole repeller. So this is the solar-powered one, and it's going to be cheaper, and you don't have to deal with it every day, right? So that's your competitive analysis on that. So you want to look at what some of the other solutions are, similar things to what you're trying to do if they exist, and how does your system compare and contrast to that. So think kind of like marketing angle, right? Kind of like doing your pitch to someone who's going to fund you, for example. Yeah?
If we made major changes because of a lack of marketability, can we talk about that?
Sure. Yeah. But don't let marketability be too much of an impediment. But yeah. If you're doing something that's never been done, that's great, right? And if you can take it and market it and get rich, that's cool. But that's certainly not a requirement for a successful SLP, right? Yeah. Because then you can donate lots of money to Clark. And a few years ago, that's what everybody was doing. Everybody wanted to do Bitcoin mining, so there are all these FPGA projects and all these parallel processing projects, and it was just 1 year, it was like 3 or 4 years ago, and then it just kind of like died out. But something got in people's brains that year. And they just busted someone in Russia, was it, a couple of weeks ago? Someone in their defense department or something was stealing time on these major supercomputers to do Bitcoin mining for themselves. Yeah. Yeah. So let's review node deletion from a tree, and let's review breadth first traversal, because these are the two points people are mostly down to at this stage. So tree deletion, remember it's recursive. Okay, if you're not deleting the root of the tree, you're going to delete from either the left or right subtree. Delete is going to return a tree, so a pointer to a T node. And if you're deleting from the left subtree, right, use the delete routine to delete, take the tree that comes back, make root left, point to that. So same thing that we do with insert recursively. But deleting the root is where we actually do the work. And our algorithm is find the largest node in the left subtree and make that the new root. All right, so here's the root. This is going to be the largest node in the left subtree. And we know how to find that, right? We did a sample of this in an ODP. Go into the left subtree. If there's nothing to the right of the root's the biggest node. Otherwise, start moving to the right as far as you can. When you can't go any further, that's the largest node. And as you're moving down to the right, we need to remember what the previous node was. And the reason we need the previous node is because this largest node is going to become the root, which means its right child is going to be everything that's to the right of the root, and its left child is going to be everything that's to the left of the root. But if this already has some stuff on the left, we're going to orphan that. So we need something to adopt the left children of the largest node, and that's what the previous node is going to do. Because we're freeing up the previous node's right child because that's moving to the root. So we want to do the following steps. So here's the root. There's some other stuff in here, right? Here's the largest node. Here's the previous. So we want to do basically three things. So largest, right, equals root right. And there can't be anything already to the right of largest, because if there was, it would be larger. So root largest right is null to begin with, so we can just set that equal to whatever's on the right of the root. And then, since the root's going away, largest left is going to pick up whatever's to the left of the root. But as soon as we do that, we've lost whatever was hanging off the left of largest. So we need to know what the previous node was, and we're going to let that adopt on its right whatever was on the left of largest. And then we can free the root.
Does it matter which one you do the first two?
No. Yeah, as long as the third one comes after the second. So there's steps to this, right? There's checking to see if the root's what you want to delete in the first place. And if it's not, you're going to delete from either the left or right subtree and then set the left or right child of root to whatever delete returned. If you want to delete the root of the tree, you have to make sure there's something to the left before you can do any of this. If there's nothing to the left, just rename this as your root, free the old root, return this. Right, so we're just kind of changing the label root to point to this. If there's at least one thing to the left, we want to find the largest node in the left subtree, and that's got some special cases. If there's nothing to the right of this leftmost node, then this is the largest node. And in that case, we simply take the right child of root and we tack it onto the right child of that node, because there's nothing down here that we need to worry about, and we free the root. If there's at least one node to the right, then we can go down, we can keep moving to the right until we can't move right any further. While we go, we remember the prior node so that when we get to the largest node, we know the previous, and then we do this business.
So the way we've got our loop set up, I guess, when we're checking to see what the largest node on the left subtree is,
Mm-hmm.
Since we have it where you only go to the right if it's not equal to null, is that really an edge case?
This one?
Yeah, like if there's nothing to the right of previous.
It's only an edge case because if this is our largest node, we don't have a previous node. And this code doesn't make any sense, right? And previous is not just the root, even though that's the node right before this, because our previous is going to get freed in that case, right? So, but it's really just a special case. If there's nothing to the right at all, just set this right equal to root right, call this your root, and you're good to go. So it's a simpler case, but it's a special case.
So the only edge cases I was able to find was the one you just mentioned, and then if there's no left subtree at all.
Mm-hmm.
Is that
Yeah, so you got three cases. Nothing on the left at all, something on the left with nothing to its right, or something on the left with at least one thing to its right. And if there's a null root, there's nothing to delete. And if the root is not what you're trying to delete, then you delete from the left to right subtree recursively. So that's 1, 2, 3, 4, 5 possibilities. Yeah, it's a lot. Mm-hmm. And it's a lot of testing, right? You can't just put in a tree and delete something and say, it works, I'm done, because you want to test each of these cases. So what else can we clarify about deletion?
So kind of just review, it looks to the left of root and then to the right of that root.
Mm-hmm.
And that's where
Yeah, so we start with just the left subtree, and beginning with that root, try to move as far to the right as possible. Right, and each time that you move down, remember what the previous rightmost node was. So that wherever you end up, you know what the largest node is, the rightmost one, and you know what the node is right before that. Right, and that's previous that you're going to use in here.
All assuming that it's in the trio.
Yes, yeah, so before, I would say before you do any of this stuff, before you call delete from your main program, call your search and make sure it's in there. Don't do your search inside delete because you're not always going to, right, be able to delete something from there. But just call search before you call delete. And in your comments for delete, say, warning, the node must be in the tree in order to use this function. That's the easiest way from the programming point of view. Then you don't have to constantly check for falling off the edge of a leaf. Yeah?
So you return just a struct tree node, right?
Yeah, you want to return whatever the new root of the tree is.
Okay.
Okay, so in this case, if we're doing this, we would return largest. Because this is going to be our new root. Yeah, yeah. Well, that makes sense, though, because we do recursion because it kind of makes life easy. So our end game is this picks up what was on the left of largest. The root goes away. Largest picks up root's right on its right, and it picks up root's left on its left. So that's what our tree looks like. All right, so let's do breadth first, traversal. And I'm going to do this a little differently this time. I'm going to actually insert trees into our queue. Okay, so this is going to make our queue look really strange. And we'll put the head over here on the left, and here's our output. And remember our algorithm. So our initial step, insert the root, and then our 3-step loop, remove the head, print the data, and then insert the children. And repeat that until we run out of nodes.
You want it to do left and then right?
Left and then right, yeah. So the first thing we do, the way we see this is we insert the root of our tree. So here's what's basically in our queue. It's a little tree, right? And what we're storing is the address of the root, but it's basically pointing to this whole structure. So effectively, we can imagine that our queue contains one entry, which is this tree. So that's step 0. So step 1, we remove the head of the queue. So I'm going to have, let's say, remove the head and put it into something called temp. So temp is going to be equal to this tree. And this is going to disappear from our queue. And then when we say print data, we mean print root arrow data, right? Or in this case, temp arrow data. So we're going to output the root of this tree, which is 20. And then we're going to insert the left and right children of this as long as they're not null. So temp arrow left is just this tree containing a 10. Temp arrow right is a tree 30, 25, 35. So now we got 2 things in our queue, 2 trees. And we go back to step 1. Bless you. So remove the head, so we get rid of that 10, and our temporary tree is just this single node tree which has a 10. We print out the data. And then we insert its left and right children. Well, the left child is null, so we don't insert. The right child is null, so we don't insert. And we go back to step 1. Step 1, we remove the head of the queue, so this comes out, and our temporary node pointer is pointing to this 3-element tree. We print the data, so the root's equal to 30. We insert the left subtree, so that's a tree containing just a 25, and we insert the right subtree, that's a tree containing 35. The queue works exactly like it did in PA3, right, except that you're inserting and removing pointers to roots, pointers to T nodes, which we're looking at as being a whole little tree here. All right, back to step 1, remove the head. Our temp variable is just this singleton tree. Print out its data. Left and right child are null, so we don't insert. Go back to the top, remove that tree. That's our temp tree. Print out the root data. Left and right child are null, so we don't insert. Go back to step 1, try to remove the head, but our isQEmpty function tells us first that the queue is empty. So our algorithm is done, and whatever we output, that's the breadth first traversal. So what else can we do to clarify this? Besides show you code. Yeah. It's lengthy.
Might as well just send us the temp first.
Breadth first? No, this is a while loop, right? While queue is not empty, remove the head, print the data, insert the children. Recursion doesn't really work well for this because recursion is inherently stack-based, and a stack-based traversal is inherently depth first. So breadth first, we gotta kind of roll our own recursion, which isn't recursion at all.
You start from the bottom and push that to stack first, and pop as you go up.
Yeah, but you have to start with the root. That's how you.
Yeah, the root's always gonna be the first thing you print.
And you can't exactly.
But if you start pushing from the bottom or from the leaf of the tree, then by the time you have your root, I mean,
Yeah, but it's not simply an upside down stack, which is what that would get you, right? It's really, as we're traversing the second level, we're remembering that the next things we want to print out as soon as we finish this level are whatever we found for the immediate children of these nodes, right? So the first thing that we remember is the first child of 10. That's going to be the first thing we print out when we're done with this second level, right? It's kind of this inherent first in, first out structure. That's an interesting question, though, if you could code this recursively somehow. So you can go back up.
Right, left, node, parent.
Something like that, yeah, yeah. Yeah.
I was thinking with like levels.
Mm-hmm.
Like start at level 1, and maybe like print that, and then you can call it again with like an extra level.
Mm-hmm.
Just go even deeper, and if it's like no, you don't print it, but then you keep going.
So you could do this with some memory. You could do a regular depth first traversal, like left node right, right? But instead of traversing, you could simply record what the depth is of the node. So you could have a series of arrays for each depth. And instead of printing, just storing the next position in that array. That would work.
Could make the height function a little easier to.
Yeah, yeah.
Depth already recorded.
Right, right. So that would be interesting.
So is that fine if we do it by depth?
No, negative points. Go back and adjust your other grades accordingly. No, I want you to do the Q-base just because it's an important thing to work through. So. But, and I'm not being smarmy when I say this, right? It's not a bad idea if you want to code it up the other way just to do it and see what's involved with that, right? And I'd be thrilled to take a look at that if you do that and want to go over it or talk about it. It's always useful to come up with things like that to do on your own. And if it's something that you come up with yourself and you've defined the parameters of it, it's more fun to work on than like an arbitrary, here's the rules and do this and don't do that and that kind of thing. It's like the stuff you work on your own is usually the most fruitful as far as learning. So I definitely encourage exploring that if you like.
The other ways of bringing out the list,
Mm-hmm.
and all that, are those just recursively like going through one side of the tree, bringing all those out?
Yeah, they're purely recursive. And
It's the same 3 lines in a different order.
it's the same 3 lines in a different order. The definition of how to do left node right on a tree is to do left node right on the left, print the root, and then do left node right on the right. Right, that's practically the definition of what we mean by left node right. The left means do left node right on the left part. The right means do left node right on the right part. The end means print the root node. And then if it's node left right, this print just goes in the beginning, and if it's left right node, the print goes at the end. Say again? Yeah, and you need to make sure the tree's not null. Otherwise, this will seg fault city, yeah.
There's so many opportunities to cite.
Oh, yeah. Yeah. Well, with all this stuff we're doing, right? All these PAs, as soon as you're tinkering with memory yourself, right, you're kind of playing with dynamite. Yeah.
Well, I don't hope this is going to happen. What would you prefer for us to turn in? Like, you can't get the breadthers to work. Would you rather this have to be like broken and turn in, or just put a comment saying you can look?
So if you've got, most of your code working, but delete doesn't work, or breadth first search doesn't work, or something like that, make a note in your submission. Okay, when you submit on Canvas, you can put comments in there. Put a comment in there and say, hey, breadth first traversal seg faults. I couldn't get it to work, right? And then I'll look at your code and I'll take off some points because breadth first search doesn't work. But what you don't want is, breadth first search had a problem in it, and so now nothing works. Or I try to compile and I get a compile error and I can't get an executable. Don't do that, okay? Get as much of it working as possible, but if there's parts, if you try to delete and it blows up or it goes into an infinite loop or something like that, just let me know in the comments so I know to expect that. And you lose points for that piece of it, but the rest of it's fine. So, but make absolutely sure as much of it works as possible, right? Including compiling up to an executable. And include everything in your tar file, and don't corrupt your source files before you put them in your tar. Yeah. Yeah.
I don't remember which one I forgot when I turned it in, but last time.
Yeah, I think I remember that.
So I'm kind of curious, how exactly do you corrupt the tar file?
Oh, it's really easy.
Like, you always talk to like, make sure your tar file never corrupted, but I'm not even sure how to do it.
All right, that'll do it. What you really want is tar cvf, pa5.tar, and then the list of files. If you don't have that, the first .c file is the name of the archive. And so if that's, main.c, main.c is no longer main.c, it's a tar file.
Don't put delete first.
Yeah. Yeah, call it z delete or something just in case.
Terrible to have first too. That's a long
Mm-hmm.
to redo. I just push it
Yeah.
back up to the server before I do any tarring.
Yeah. Yeah, keep backups, use Git, put them on flash drive, something, right? Have some kind of backup strategy because stuff happens. I munged my files a few weeks ago, late night doing something, and I tried to remove star.txt, and I got a space in there. So I removed star space .txt, and bye. All right, did you have a question? Okay, cool. All right, so let's talk PA5. All right, see you later. Let's talk PA5. All right, so PA5 is a group project, first of all. So groups of 1, 2, or 3 people. Can't have 0 people in a group. Maximum 3 people. I'm going to stick to that. So find your friends quickly. So group-related notes. Make sure you have in the beginning of your main program comments naming each member of your group, full name, first name, last name, please. And tell me what each person in the group was going to work on. This might change as you get into your project, but before you start coding anything, talk amongst your group members and decide how are you going to split up this work. There's lots of pieces to PA5. So make some initial decisions. I'm going to work on the max val function, and you're going to work on reading in the knapsack file and doing all the error checking, and you're going to work on the main program and the command line parsing. And then we're going to put our pieces together, okay? Figure out how you're going to partition this. And I don't mind if that changes as you go through, right? If you're working on the max val function, you got a problem, somebody else starts helping you with it, that's fine. But I want to see some planning ahead of time about how you're doing this as a group, okay? As opposed to we all got together and had some beer and wrote some code. And then one person upload the tar file to Canvas by the due date. Okay, and please make sure it's only one upload. Otherwise, whichever one I happen to grade, that's the one that I'll grade. Okay, so coordinate on that. All right, so you are doing the 0-1 unlimited knapsack problem, which means that your program is going to be run with a single command line argument, which is how much can we store in our bag? What's the weight capacity of our bag? Okay, and then it's going to look in your current directory for a file named knapsack.data. It's going to open that file and it's going to read the following triples: a weight, a value, and a name. Okay, so a mouse weighs 1 pound, costs $10. Cell phone weighs 2 pounds, costs $25, and so on. You're going to read those in. You're going to have to store them somewhere so that you can get the value and the weight of each item. So you definitely want to use some structures in here, right? Use a structure for storing the knapsack information. Probably use a structure for storing the solutions to the problem, because you're going to want not just what the maximum value is, but what the inventory of items is that gets you that max value. So your max val function, I've been calling it max val in class. This is basically what it does, right? Loop through all the possible first items, take the value of that item plus the max val of the diminished capacity bag. So the original capacity minus the weight of that item is your new capacity. Find the max val of that, add the value of the item you put in your bag. That's the value you get if you put that first item in your bag. Find the largest value of all of those. That's the max val. Return that as the value of max val. And you're going to want to keep track of how you got that. So you want some kind of structure for storing the information about what's in your bag. And one way to do this, if your items are indexed, item 0, item 1, item 2, you can have an inventory array. And entry 0 tells you how many of item 0 you have. Entry 1 tells you how many of item 1 you have, and so on. So initialize that array to all zeros. If you put item 5 in your bag, increment inventory bracket 5. If you put item 2 in your bag, increment inventory bracket 2. And at any point, you can look at your inventory array, know exactly how much of item 0 you have, how many item 1s, how many item 2s, and so on. And when you're done and you come back from max val, your final inventory tells you what you put in your bag to get that maximum value. So max val is not just going to return an integer. It's probably going to return a structure that contains the max val plus the inventory that gives you that max val. All right, you definitely want to be caching your values. So make a save array, consult that before you recurse. If you have to recurse, save your final answer in that array before you return. Otherwise, the test cases I use will never finish. And I'm going to ask you in the very beginning of your program, after you read the knapsack.data file, print out the contents of it in some nice format so that the user can see what the set of possible items are in their bag. Run your algorithm to find the max val in the inventory, and then print out your solution neatly. So here's a knapsack.data file sitting in my directory. So there's a PA5 sample under /temp. And if our capacity is 1,000 pounds, it shows me the set of options, set of items I can choose from, tells me the bag's capacity is 1,000, highest possible value is 11,200, and you get that by putting in 200 books. Okay, so that's what your program wants to do. And you can put in any capacity you want. And it always likes buying books. How much does a book weigh? Well, the book is 5 pounds. Okay, so.
Wait, so it should try something?
So there's a new car and 99, 2 new cars and 99 books.
So, you know, with the 102, then, doesn't that have extra space in it?
You might have space left over.
So
Well,
it won't pick up a pen?
No, you should. Do I have space left over?
In 102, it picked up, oh, yeah, okay.
Yeah, 510, that's
Okay,
exactly.
I thought that's what you put in.
Yeah. So if we set this right, so 508, we got a pencil, 100 books, and 1 new car. All right, error checking. So I want your program to be as bulletproof as possible. So possible error conditions if you don't specify the bag capacity. If you just run your PA5 but you don't give it an argument, that's an error. If you give it an argument that's not an integer, that's an error. If you give it a capacity of 0 or negative, you can treat that as an error, or you can run your program and come up and say the maximum value is 0. It's up to you. Okay, just don't blow up, don't seg fault, and don't do something random. If I run PA5 with a capacity of -10, don't solve the problem for +50 capacity, right? So do something that makes sense. If the knapsack.data file contains corrupt information, if the weight's not an integer, if it's got the weight but it doesn't have a value, if there's a blank line in the file, if the file itself is missing, right? All of these things are error conditions. Again, you only have to be as good as Sscanf. So if there's extra stuff at the end of the line, I don't care. Okay, but if Sscanf won't parse it, print an error message.
Putting in custom text files.
So I'm going to have my own test files. There's a test file under /temp. There's one in the assignment, and you can make up your own and experiment. So simplifying assumptions, maximum of 128 items in the knapsack data file, which means you can statically define your arrays for storing weight and value and name. Maximum capacity I'll ask you to work with is 1024. So your save array can be statically declared 1024 or 1025. And the name of the item, that third column of the knapsack data file, 32 characters max, no spaces. So you can parse it with just a %s in Sscanf. All right, and then one person in your group put it all together in a tar file, including a make file, put it up on Canvas. So if you run this without a capacity, I give a usage message. If you say ha ha ha, if you say -20, so I printed an error message. And if your knapsack has strange things in its file, right, so I can print an error message when I'm parsing the knapsack.data file and just kick out of the program. So if you don't save your values, this will take a really, really long time, right? So this is for a capacity 100 on that same file, and it's just going to sit there and chew up the CPU. If you save your values, then it'll come back pretty quickly. So questions about this? Mm-hmm.
Is there an easy way to scan one knapsack file the second line? Because Sscanf scans
Mm-hmm. Sscanf scans from a string, right? So it scans an entire string. So open your file, use an fgets to read the first line, use an Sscanf to convert it. And the way it's set up, you can just do %d, %d, %s. Save it in an int pointer, and a string, car pointer.
I guess what I'm asking is there an easy way to fget string the second line and specify like second line of the file?
Not that you want to do. You can get into seeks and things like that, but my recommendation is suck everything into memory. Right? So make an array of weights, an array of values, and an array of names, or an array of structures where your structure can store a weight, a value, and a name. Right? And before you do anything else, open the file, read it in one line at a time, store what's in that line in the appropriate spot in your arrays. Get to the end of the file, close it, you're done with the file. You've got all that stuff in memory.
So you just call fgets for each line?
Yeah, so loop until fgets returns null.
So it won't take the same line again?
No, fgets always reads the next line of a file. So fgets goes up to a new line, And then if you call fgets again, it'll read from the next place in the file until it finds a new line. Yeah, yeah. Yeah, so when fgets returns null, then you've hit the end of the file. So your typical loop can be something like while null is not equal to fgets. And in here you do your Sscanf. Yeah. The main reason being file I/O is just really, really slow compared to memory access. So you don't want to be thrashing the disk. But that would be an interesting variation. See how that degrades performance.
So this program is going to need to be able to run. It's not going to return. It's not going to end after a single entry of the weight. So you can start.
No, it's run and done.
So it's not like most of the other ones we've been doing.
So PA5, tell it how much weight you want, figure out the answer, print it, you're done. Yeah, it's not an interactive command line kind of thing.
I wasn't sure if you were saying put it in memory so that if you do it again with the new capacity.
No, put it in memory so that while you're going through this whole, max val equals all of this stuff, you're just pulling out your weights from, right, while you're doing max of value of item 1 plus max val of capacity minus weight of item 1. Right, that these you can just read out of an array. All right, makes sense? So